Hello, everyone. This is Research Jam number 18 and the last one of this year. This is my 18th time of saying this line and having it recorded. So I find it a little boring, but I'm sure every time is someone's first time. So kind of want to say it with as much energy as possible. So we are a community of independent / unaffiliated / goofing around researchers trying to study machine learning topics and trying to make progress in research, either it's towards a paper, blog post, open source software, whatever goes. And the jam is where we gather people and they can present their intermediate results or final results or any progress they've made or any confusions they've run into to gather feedback and thoughts and collaboration opportunities and just have it out there and for them to feel good about that they've accomplished this presentation. So every time there are different numbers of submissions of speaker submissions, and this time we have 2, which is great. I love this number. So we're not really restricted by time. I give them each 15 time-ish, but we can also ask questions during or after, depends on the speaker. Okay. With that, we can start with the first speaker, Soumya. Okay.
What was the architecture of your neural network?
It was the transfer.
Okay, we have 2 presenters, but only one opted to get recorded. So let's move forward to that one. It's by Alex and Alex.
Okay, Roseanne, do we?
Alex.
Slides open. All right, sharing screen.
Yep, looks good.
So this one's going to be a bit more high level, I think. We are basically looking to train an AI for a board game called Backgammon, and we'll talk about that. Yeah, so using reinforcement learning. So first, like a little bit of background. Backgammon is a 2-player game. I'll show you a little bit what it looks like. It's 0 sum, so perfect information if you know what this means, and it's stochastic, so players roll the dice before they play their move. It's a very, very popular game. Europe, but hundreds of millions of people play worldwide, and many of them are competitive. I think the game is getting more popular. I personally started playing it myself during COVID as a kind of a hobby, and I got a bit addicted to it. For backgammon, in particular AI, I mean, all games AI is important, but for backgammon, it is particularly critical for a couple of reasons. First, mainly middle-class players and even aspiring players, they use the computer to train. So the computer is the best player right now, and there are these difficult positions, and you just use the computer to get the answer. And then you sort of try to understand what its reasoning is, and this is how people get better. The second thing is there is a lot of luck in an individual outcome of a game, and so you can't really use like ELO to rank players. The organization that gives out awards, so for example, if you want to become a grandmaster in backgammon, the way that they determine whether you're a grandmaster or not is they look at your matches that you played in official tournaments, and something called the World Backgammon Federation analyzes your games with the computer, and the computer says like you have a certain error rate, and if your error rate is low enough, then that's how you get to become grandmaster. So the computers are sort of very critical even to determine how we know how good people are. The current software that they use for this is pretty old, and as far as I understand, the models probably haven't been trained in 10 or more years. There's known positions where it doesn't. We don't think the computer is not correct, and so this seems like a sort of low-hanging fruit to me. So, and right now, I'm training new models. I'll get a little bit more to like what we think needs to happen for that. Just mention again, this is some more things about the game that make it interesting. Is so if you're familiar with like the research from Go and chess and whatnot, you might be familiar with like the branching factor of a game. So this is in general like how many, if you're trying to do a game tree search from a certain state, how many like next possible states are there after one move? And in Backgammon, this is very high, so it's sort of as big as Go, about 400. That also makes it difficult to use like more traditional algorithms that are machine learning based, that alpha, beta, pruning, search type things. So the other sort of unique thing that we came across when we were doing this with Backgammon is that I need to explain this, but the Backgammon in some sense has a lot more actions than either chess or Go, and this is causing us a problem when we want to apply some algorithm like AlphaZero to it. So that was sort of the main thing I wanted to discuss in this talk, but also happy to sort of just discuss the general high-level problem. So what I mean here by possible actions is not possible actions from a given state, but total number of possible actions from any state. So as a thought experiment, you can consider tic-tac-toe. It has 9 possible places to put a mark, and you can either be player 1 or player 2, like the player that puts the X's or the O's. So in tic-tac-toe, there's 9 possible actions for the first player and 9 for the second player, so there's 18 total actions. And these are available from any state. So some of these actions might not be available in a particular game at a particular state. But if you're trying to model all the possible actions, then there's 18 of them. And this is what they did with chess and Go, what AlphaZero did. But Backgammon, because of the dice and because of the rules, there's actually 750,000 possible actions, about that many. So this becomes sort of a problem if you want to have a network that has say 750,000 outputs. Right. So anyway, I'll go into more detail of this, but
yeah, like is there some reason that you want to represent the action space this way as opposed to a slightly smarter, much smaller way of representing the action space?
Yeah, I mean, I don't have a good smart way of doing it smaller than that. All I can tell you is the way that AlphaZero works for Go and chess is that they try to model the actions in the output of the network. I'm not sure if I completely understood your question.
It just seems like if you wanted to, you could engineer a network with a much smaller output layer to still be able to represent all possible relevant actions, maybe the legal ones, get rid of a bunch of actions that would never be legal or would.
Yeah.
But then it's more heavily engineered, and that maybe your point is you want to make it not engineered.
I think that is a good, I mean, this is actually the sort of similar to the idea that I had for what we want to maybe want to do next. And I have another slide for that. So we could discuss it there again. So I think what you're saying is sort of similar to what we were also thinking, but we haven't gotten around to doing any experiment on that yet. We did find like AlphaZero code, and we're just trying to use that out of the box. And so they actually did a kind of a hack thing to have less actions, which we don't like. And yeah, well, maybe let's shelve this question till the later slide. So the final thing I'll mention is the competitive professional software on all known methods to get Backgammon to world class requires you to use reinforcement learning, at least at the beginning. Now, sometimes later they switch to kind of a supervised learning approach. but to jumpstart the supervised learning approach, you need RL. And this game was actually considered one of the first major successes of RL back in the 90s. So, all right, here's a picture of like the board in the game. So you have two players, and the one player has sort of the brown checkers, the other player has the white checkers, and one player is moving one direction. So here brown is moving clockwise, and then the white checkers are moving counterclockwise. And your goal is to sort of get all of your checkers all the way clockwise, all the way into the upper right quadrant. Brown's goal is to get all their checkers into the upper right quadrant and then get them off the board. And so here the brown rolled 2 6s. So I don't know if you can see this on the left-hand side, there's a dice on the board, and they're moving their checkers 6 squares. So sort of this is how the game is played. And it does have a special rule. So normally if you roll a dice like a 6-3, you can move one checker 6 and one checker 3. And there's a special rule, which is if you roll doubles. So here they roll double 6s. Now you can actually move 4 checkers 6. So you can move one. So it's like you rolled 4 6s instead of 2 6s. And that's what creates a large action space. So if there wasn't that special rule, then the action space would only be around 1,000, and then maybe you could apply AlphaZero. I don't know. There's some other things that came up in our experiments that make me question that one as well. But anyway, for this particular action situation, because of this rule, there's 750,000 potential actions. It's like you're rolling 4 dice. And there's 25 squares on the board. So the way I'm getting that is just taking basically 25th to the 4th.
Just a quick question, Alex, about, because I don't really understand the game, but
yeah,
like this double situation or even the single one, it's either, if I understood correctly, if the die faces don't match, then you basically can move 2 checkers, each one at the face value of one of the die. And if it's double, then it's you can move twice as many, let's say.
That's right.
That's correct. So when you think about these actions, is there any reason that you have to collect them all at once, or can you just treat it as, okay, I will now do it 4 times. I have 4 turns here because I rolled a double. I have 4 independent turns before the board switches to someone else. And does that simplify anything?
Yeah, this is a good question. So this is sort of the hack that, like, we found some Google code that has AlphaZero, and they even have Backgammon. And so this is what they're doing. When there's doubles, they give the player 2 turns. But this seems very suboptimal from the learning perspective, because now the network has to figure out, like, okay, when my dice are equal to each other, somehow I magically get 2 turns. When I don't have dice that equal each other, it's just a normal game. And this feels much, much harder to learn just intuitively than if you just get 1 turn per call to the network in the reinforcement algorithm. So it's sort of like making the problem much harder, I think. But it's a good idea, of course.
I see. And then is there any advantage, like, is there any advantage to, well, let me put it this way, maybe it's information, but even in the case where they don't match, they're 2 independent moves, so to speak. Is there any advantage to treating them as 1 move, or 2 independent moves are equivalent in terms of the outcome of your actions, so to speak? I don't know if that makes sense or not.
Maybe. I mean, so I think from the perspective of the player playing the game, this is 1 move. You roll double 6s and you get to move potentially 4 checkers. There's no restriction for you. You can move 1 checker 4 times, but you have to use all the 6s. You have to use 4 6s. So from the perspective of the game and the player, it's just 1 move. And so, yeah, if you give the network 2 moves, I think that will just make it harder to learn. And it's already pretty hard to learn. So I can give you some results that we have with trying to learn it.
I might be saying something simpler than that. So
Okay.
let's say even in the case they don't match. So I can, of course, from my perspective, it's a human, it's one turn. But if I treat it as they're two independent moves, right? I get to make one move, then I get to make another move. I would still make the same choices as if I treated them as one unit. So I can simplify the whole thing by saying I'm only moving one checker at a time. And maybe you already do that, I don't know, but that's what I was wondering. And yeah, without knowing the game, don't know if that really makes strategic sense or not, but that's what was in my head, is simplifying all the way down to each one is an individual move. I might have two, I might have four moves, but as individuals.
I was just going to add, I looked up Tesoro's old project. I hadn't looked in a long time. And the output is just one value function node. It's just saying, what's the probability of win from this state? There's not a million outputs. So it's a very different design than AlphaZero. It's just one. And I wonder if there's some, just wonder what you thought of that. Or
He is not modeling a policy directly, and that's why he doesn't have one output per action. And absolutely, we've thought of this, and I agree that like Tesoro's work is sort of like where we're starting with this project.
It's a very key difference because if you're only saying the probability of winning, then you don't have to deal with all these actions at all, and you only look at the board state. And arguably, that might be why his result worked really well so early on, even with very limited computational power. Why, basically, if you try something with more actions, then it doesn't work. And one thing to note is that AlphaZero, I believe, it does a combination of cross entropy loss between MCTS and the policy and a value function regression, a squared error, but it does value function error and not Q value function error. So it is also modeling the board state for the value function. So it may also have that simplification. So it could be very important as a simplification.
and then you have to do your search on top of this, right? And you have to say, oh, what if I did that move? Then I'd have this board state. Let's evaluate that. What if I did that move? I'd have that board order. Let's evaluate that. But then you'd have, because what you're saying is most of your valid actions are not valid. If you had a short list of valid actions, maybe you could loop through that in some reasonable amount of time and avoid your giant action space and giant output policy and giant. Or you have some kind of embedding thing where you embed this giant action space into some embedding, and then you turn it continuous and you try to read out your discrete action from this small continuous.
I don't know how all these factors would stack up against each other, but to use the value function approach, you would also need to simulate at every step, I guess, all possible roles. So that kind of adds extra branching. Whereas maybe just modeling the Q function, you would be modeling the average effect of taking this action. Just to throw another idea in the ring in terms of how to represent the output. So I see there are 24 stacks positions. What if you represented the output of the network as the first move in a turn of either 2 moves or 4 moves, depending on whether it's doubles? You kind of like click on or select one of these 24 slots, and if you're the black player, you click on slot 13. That moves that checker, the number shown on the dice, maybe the lower number shown on the dice if you want to disambiguate. And then your network has 96 outputs, so up to 4 clicks are allowed. For most turns, it only uses the first 2 clicks, and the second 2 are irrelevant. For doubles, it uses all 4 clicks, and that's a much smaller output. Would that work as an output?
So the sort of pseudocode, or it was code that we found published by Google for AlphaZero, requires you to have kind of a one-hot representation. It's sort of the action, all the actions are sort of numbered. And naively, if you only had 2 dice, and like you said, there's 24 positions, so it's sort of like 24 squared possible actions.
Right.
And I guess you're suggesting to have the output of the network not be a distinct one-hot representation for each action.
I was proposing you have 24 times 4, so 4 one-hot things over 24 each, rather than like 24 to the 4th. Like,
yeah,
avoid the cross product.
Thought about this. We haven't done experiments with that, and there was some concern about doing that.
In general, some way to factor the action space so that you had like actually multiple actions at once, and together they give you the giant action space, but individually they're much smaller. I'm agreeing with what you're saying, Jason, but I think there's probably many ways to formulate the factoring. Man, I know that's not what they do in AlphaZero, but might be able to make it work.
Right.
Yeah, so the TD-Gammon was this, people may be familiar with this already, but sort of, it was the first computer AI that had any kind of good performance. And it was a reinforcement learning approach in the 90s based off of TD-Lambda, if you're familiar with that. And it used a neural network, so it was required to have a nonlinear approximator. One thing that we've been working with, we're sort of like, well, TD-Lambda, as described in Sutton's book, is about learning a value function for a fixed policy. And so, if you read Tesoro's work, it's like, well, how is he learning a new policy? And it turns out that if you reformulate the math, it turns out TD-Lambda is just Q learning. And this wasn't exactly clear to us when reading the papers. It never says it's Q learning, it says it's TD-Lambda. I thought this was a sort of an interesting mini result here. So it is a special case of Q learning. So you see, as you're playing a game, and here, like, the way it works is it plays against itself during training. So the computer plays against itself in this state. It sees it takes an action, and then it sees the next state. And generally here, the initial state, like a certain player is on roll, so Brown takes an action, and the next state, the other player will be on roll. So some of the ideas that you guys have been suggesting were like to have one player make multiple actions, and then that would break this, and so that might make it harder to train. But anyway, for Q learning, so you see these observations, and then you update your network. So your network takes some state action pair and tries to model the long-term expected probability of basically winning the game from that state. And so you update your model to be more like its future self. So you sort of look ahead in time and say, what does my future self think the next best state is, and or state action pair? What Tesoro did, though, is interesting, is that he used a particular way of representing the state action pairs that he sent to the network as sort of not what you would normally think of if you were just doing this from scratch. And that is it. It seems to be extremely clever and useful, this way of representing it. So I have a little bit more time. The way he did it is, instead of like trying to encode the current state and the current action, what he just does is, for a given state in action, you just take that action, and then you have what the board looks like after you take the action, and you feed that thing into the neural network. What you're feeding into the network is sort of, you can't even recover the original state, but it's very, very powerful on how it trains. So one experiment we did is, we found some code for TD-Lambda, or sorry, for TD-Gammon, and we didn't use that representation. And we use something more like what you would consider natural. And there's some results down here at the bottom, but you can see like regular TD-Gammon after 6,000 self-play games gets to kind of a beginner level of play, and after 2 million, it gets to like sort of a strong intermediate level of play. And if you don't use that clever representation, after 600,000 steps, you're still kind of not even really at beginner yet. You're like beating random, but you're not very good. So we think that backgammon may be particularly sensitive to the input representation. Now, this isn't deep networks. We haven't gotten to that. I haven't gotten to that yet, but maybe with the deep network, you don't need this. This may not be an issue, but it was sort of surprising for us. Okay, so AlphaZero and DQ. So we talked a bit about this a bit. So there's a lot of other differences between AlphaZero and TD-Gammon. AlphaZero has the MCTS, and like it's using some more fancier techniques from machine learning. But the big issue that I seem to think is this action space thing. I will mention we did find this code that Google released, and it's called OpenSpiel, and they have a backgammon environment, and they have DQN with DQR, they have AlphaZero, and we tried to run that, and it just doesn't work at all, essentially. So we're sort of trying to figure out why that is. So there's this action situation, but there's probably some other reasons why it's not working. All right, final slides. Maybe we can have this discussion again. So on the left-hand side is TD-Gammon. So you have your state action pair, you send it to the network. There's about 100 inputs here, and the network tries to model the Q value, the QSA. In AlphaZero, which is the middle one, in AlphaZero, you actually don't send in the action at all. You just send in the current state. There's also about 100 inputs now. There are different inputs. Obviously, they don't have the action. And then it gets sent to two networks that has some shared weights, a value network and a policy network. So the value network tries to give you the value of the current state. And then the policy network, again, has one sort of output per action. And because it's trying to work for any state, now we have to have one action for any possible, or so one output for any possible action from any state. This is the issue. So we have like a lot of actions. This seems totally intractable if you just do it straightforward. So one idea is to still feed the state, but also now feed in an action to the network, and still have a value in a policy network. And now the policy network would just need to spit out or send out one output. I should mention here, what is the policy network? What are these outputs? So these outputs are probability that I should take this action from the state. So it's not like a value function anymore. It's just like, well, if you think action one is the best, you would have a 1 for action 1 and 0 for all the others. But usually it's sort of like a stochastic approximation. And so this is one idea here on the right. We haven't tried it yet. We're sort of interested in people's feedback on this.
I just want to ask a clarifying question from my memory about AlphaGo, actually, not the AlphaZero paper per se. Maybe it's different. But my recollection is that what gets output is for all the possible places you could put a stone on the board, including illegal ones. What is output is the probability would be a good move. And then some subset of that is selected. And then that's what they run through the tree to determine which one they would ultimately take. And then in your case, it's a little different because it's not just putting something down. You're taking something that's already on the board and moving it to another place on the board. Just to clarify, so to understand what we're looking at.
Yeah, that sounds all correct to me. It's also my understanding.
Okay, all right, thanks.
So it sounds a bit, the last one sounds maybe like DDPG, like deterministic policy gradients, where which is designed for continuous control. So you can't output a Q for all your continuous values. That's just not a feasible thing to do. And so they do a different architecture with DDPG. And I think they actually put the action in at the bottom, in the beginning of I put it in the network. And it's been a while since I looked at that, but I think you might look in that. There are genres of RL algorithms that do take the action as input. I think that might be useful for you.
Yeah, I mean, one trade-off of this idea of this approach on the right is, of course, that when you train or run this, you're now going to have to call the network more than once. So you're going to have to call up the number of legal actions. But there generally is not that many legal actions in backgammon for a given position, sort of between 20 and 100.
So then you'd be looping through them and putting each one through, or doing it as a giant batch, make a
Yes.
giant batch. I mean, all your actions, put it through, get your output. It could maybe even do it in one step in the GPU. It might not actually be that bad.
Right. And you know, we're not like, so here we wouldn't be trying to optimize the policy for the reward. If you're familiar with AlphaZero, it doesn't do that, so it wouldn't be a policy gradient necessarily. But I will definitely look into that because it might be useful, whatever they did for that paper.
Yeah, DDPG, and then there's some other ones that have algorithms that have been come on that line of work since then, but that was the classic. That had a very different structure.
The other thing I've sort of thought of was like just get rid of the policy network completely. I don't know how good, like reading the papers from Google, they say they needed a policy network to get good results, but they didn't go into a lot of depth of like, well, how well does it work without the policy network? Another interesting idea I have.
It seems like it would give you so much more fidelity to have the policy network. I actually asked Chaba this question last week on Twitter, and I didn't get a great answer. I don't think he gave a great answer, but he said there's a bunch of reasons. But in my impression is it just gives you so much more fidelity, because a little bit of noise in your value function is going to throw you way off. Whereas if you a little bit of noise on your policy might actually be a lot less bad.
Isn't it also the case that you need the policy network because you're trying to limit the breadth of the tree search?
And
And
that's
the policy
fundamental to
network
the
does
whole.
that.
Yeah, absolutely. It's fundamental to the whole tree search. That would all fall down if you didn't.
You can, if you have a value function, you can get a policy, right? You take the max or whatever, you can convert a value function into a policy. So if you need a policy, and as long as you have a value function, you can, I think you can still do MCTS and whatnot. I think like one of the ideas is that you sort of have two networks and you're training them both at the same time, and they're sort of like dueling each other, and this might help the whole system converge and get to a better performance.
I think they just use one network for both opponents and also for the value and policy. I think it's all just one network playing in the mirror.
Right, but there's a policy and a value portion of the network, right? And they're getting trained at the same time. And the policy is sort of being fit to match the value function. And I can see that this might provide some stability or variance, lower the variance of the training. And like what you do find with TD-Gammon sometimes is that you'll run it, and if you don't get the settings right, it gets to a certain level of performance and doesn't get any better.
Well, the original TD-Gammon didn't even have a replay buffer, right? Because that was like pre-DQN, so they didn't even know about that stuff back then. So it was really hard for them to do anything stable. And then on terms of the policy, I think in the way that they frame the Go AlphaZero is the policy gives you such a nice probability on every move, whereas how would you get such a clean probability off a bunch of values? You could get the max easily, but how would you break it down to the probabilities? I don't really know what you do, and the probabilities are quite central to how they formulate the problem.
There's something called Boltzmann Q learning where you take the exponential value function and you use that and you do like a softmax over that to get probabilities of actions.
Oh, good one. I wonder if that would map well to real probabilities.
There was one thing I remember. Sorry. So for my hypothesis for why the policy is important is that if you ever play chess and you look at like Stockfish or whatever, there are some very difficult positions where if you let it run for just a short amount of time versus a long amount of time, it'll actually change what moves it suggests. So my interpretation is that the policy network, you can have a value function, but that's a very short-sighted view of the game because we don't have like a perfect policy. But the policy is used, it's not actually used it's specifically used for the MCTS planning, and it's used to choose actions, but it doesn't actually take that, it doesn't use a policy to take the final actions, it uses the MCTS planning. So I think the AlphaZero term, there's a cross entropy loss between the MCTS policy and the neural network policy. So I think what it's trying to, the benefit of it is that it is trying to learn longer term planning. At least that's my particular interpretation. And one of the interesting things about backgammon is, or if you look at chess, you can run Stockfish for a position and like maybe in 30 seconds or something, you can go down to the depth 22. the most modern or the most state-of-the-art backgammon neural networks, they only go to depth to like 4 or something like, or maybe 8. I'm not sure. It could be half moves or moves. So it's very, very low depth compared to chess. And I know chess grandmasters, when they analyze positions, they'll go to like depth 50. This is because of the whole action space or the branching factor explosion. It's literally impossible to do in backgammon. You cannot search like as many positions as they're doing in chess at all. The computational budget will be extremely high. And when I ran AlphaZero experiments, in order to run like each training step in a reasonable amount of time, I had to reduce the simulations, because I was just running on my computer, to 64, and that is barely sampling each action once, right? Or if you have like 40 different actions, you might be sampling every action 1.5, so you're not even looking 2 moves ahead. But I can make it larger. I can like increase it by a factor of 4, but then I'm only looking 2 moves ahead. So there's enormous scaling problems for if I try to implement, if we try to use AlphaZeros or the tree search.
I'm curious about your guys' next steps. Are you in the process of implementing this idea on the right here?
Yeah, I think that's where we're at right now. We're sort of deciding what our next step is. So that's the current progress. I think that's our current best hope, we think, right now, is the one on the right.
I'm stuck on one thing, and it's that so the DeepMind's OpenSpiel framework for DQN, and maybe there could be a bug in it. It uses action spaces where you only use the first checker position, so it comes down to 26 squared in terms of the action space. So because you pick each checker to move, or each checker position to move. Still, so when I run their DQN algorithm and I've played around with it, it doesn't get better than random. If I run AlphaZero, it'll get to about 50 error with some better games, which might be like 20. So it actually has learned something. It can eventually reach the maybe intermediate level, but the DQN doesn't work at all, which is a little strange because TD Lambda, or the original TD-Gammon, it actually got to like it matched like master level players. So this small difference of increasing the action space, or it could be some architectural difference, and suddenly it just fails completely. And I am very confused by this. And I'm starting to suspect that there has been no DQN worked for Atari games, which was sort of a single player game. But I'm starting to suspect that there have not been actual successes for board games for DQN at all. And this is, I don't know if people know about this, but I haven't found any literature searches where it's been successful. And
I tried DQN for Connect 4, for 2-player Connect 4, and it was brutal, but I wasn't very good at tuning it, so that's not a really good data point.
Yeah, I mean, I guess,
Also, vanilla DQN is very old-fashioned now. There's a lot of better things on top of, at least on top of Q learning.
it's really weird. And maybe they just got really lucky, or had a lot of foresight with the single value function. So maybe they just chose a good approach in Q learning. Maybe it works for Atari games, but it just doesn't work for 2-player games. And one other thing to mention is that this whole dice roll things. So one of the problems is that, like, if you model it through like 4 separate actions or 2 separate actions, the neural network has to figure out whose turn it is. As you play the first dice roll, then you play the second dice roll, and okay, maybe that's achievable. But the bigger problem is if you run something like Q learning, if you remember the equation was based off of the Q value, and then you regressed upon the best action for the next opponent. One thing is that you could say, well, it's zero sum, so there's some symmetry. So we could sort of take the neural network for the next player for the next move, and then just flip the sign. Because now what becomes the best action for the next player, that's actually your worst possible action. So you could try that. I tried that and it didn't work that well. It didn't really help that much. But if you have multiple actions in a row, it's like becomes really confusing about flipping the sign, because like, do you flip it to, I don't know. It's really weird, because if it's your turn again, then you want to Q max. If it's the opponent's turn, you want to Q min, and it's just like very unwieldy. There's sort of implementation issues with that. There's a lot of small implementation issues, but yeah.
I know we're out of time. I'll just say one last thing. I know that manually tuning DQN, the original DQN, was a big part of getting it to work on Atari. That one dude, the main author of the paper, did all sorts of magical tuning that would be very hard to reproduce. Just throwing that algorithm at Atari would not work. So this guy was, people said he was a genius in tuning. Well, I don't know. Maybe you need a genius in tuning the Tesaro thing too to make it work. And that didn't come through in the paper.
Yeah, I guess another next step for us is to, because you know, TD-Gammon does work and it is sort of Q-learning. So, what is Q-learning? So, making small changes to that to be more like DQN and seeing what works or doesn't work is another line of future research for us. But what we really want is to do something like AlphaZero. That's the goal. We think that that's just a better algorithm. And I think, thanks everyone.
I'm looking forward to hearing any updates if you guys want to show up next time and let us know how it's going.
Thank you for
I just want to
presenting.
say I really appreciate you guys doing this. It's so cool. Like there's so many barriers to entry for so many people, and it must be a little chaotic for you guys as well. You never know what you're going to get, but just to have the guts to do this, I really appreciate it. Hopefully, I'll be on the presenting one day.
Thank you. Makes me feel good. All right. Thank you, everyone, and see you next time.
Thank you.
Thank
Bye-bye.
you.